Hello everyone, and thank you for attending today's webinar, Streamline Deep Learning for Video Analytics with DeepStream SDK 2.0, hosted by James Junn. Before we begin, we wanted to cover a few housekeeping items. James has created a wonderful presentation for us today. This content is pre-recorded, which allows him to be online to answer questions real-time via the Q&A widget throughout the event. At the bottom of your screen are multiple application widgets. All of the widgets, as well as the slide area, are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you have any questions during the webinar, please submit them through the Q&A widget. We'll try to cover as many questions as possible during the Q&A portion, but if there's any we don't get to, please post them on the forum to keep the conversation going. Be sure to check out the resource list for links to the developer site, forums, wiki, and more. And if you run into any technical issues during the webinar, you can find some answers to common questions located in the Help widget at the bottom of your screen. An on-demand version of the webinar, as well as the slide deck, will be available approximately 1 day after the webinar and can be accessed using the same audience link that was sent to you earlier. And with that, let's get started.
Thanks, Lon. I'm glad you've decided to attend this webinar. I'm one of the product managers at NVIDIA, and today I'm excited to talk to you about the latest version of the DeepStream SDK that is targeting our Tesla GPU product line. Let's get started. We have a lot of great content to cover. Here's a list of topics I'll discuss in this webinar. I'll start off by covering some of the popular use cases for intelligent video analytics, and then go into the typical flow for building out these applications. Then, I'll discuss how DeepStream can help simplify and streamline your development by looking at the fundamental operations, metadata, the pipeline architecture, and the plugins that make up the core building blocks of the application. I'll show how we bring all of these components together to build the included reference application, along with some key points on performance. Finally, I'll talk about implementing custom plugins and provide guidelines on mapping your custom use case to the DeepStream architecture. Feel free to submit questions throughout the webinar, and we'll discuss some of them live towards the end. Video and images represent an enormous amount of data that can deliver vast insights in our cities. Meaningful insight can be gleaned from the video, and we are starting to see several interesting use cases that can benefit, such as frictionless access control for faster boarding of airplanes and trains. Public transportation agencies are working to more accurately determine the occupancy of train carriages and buses. It's also helping to make parking management more efficient by minimizing the search for an open spot and more accurately determining the duration that a space is occupied. Other companies are understanding the flow of traffic through intersections to better design roadways and reduce traffic congestion. On the retail side, video can help understand customer behavior to provide richer experiences and optimize store layouts. Logistics companies can keep better track of metrics, such as how long it takes to load cargo onto an airplane, and identify areas that can be more efficient. These are just a handful of the applications that are being worked on. Now, I'd like to take some time to send out a poll question so we can better understand which applications you guys are interested in building or perhaps developing already. You can select one or more of the below options, and I'll give you guys a moment to answer that. Traditional methods for video understanding have simply not delivered the performance and accuracy needed to support real-time actions in diverse environments. Modern artificial intelligence techniques like deep learning can help transform video into meaningful insights at scale. Deep learning allows solutions to be deployed across a variety of difficult conditions like rain, snow, and dynamic lighting conditions. We've come to understand that all of these applications utilize a common architecture and basic building blocks. This includes collecting video and image data from various sources, decoding bit streams, pre-processing like resolution scaling or color space conversion, running many neural networks for extracting insights, encoding, and visualizing the data. To simplify the solution development and deployment of these applications, we built the DeepStream SDK. I have another poll question for everyone. We're interested to know which input sources your application may use. Again, you can choose one or more of the following options. I'll give you a moment to answer. The goal of DeepStream is to accelerate development of IVA applications by allowing you to focus on the core deep learning networks in your IP rather than designing an end-to-end solution from scratch. DeepStream can be described as a framework where every function can be mapped to a plugin or module, and the application is essentially the glue to all of the plugins in a graph. Graphs can be tailor-made to the imaging and video requirements for your specific application. To get started quickly, developers can use the included reference application, which I'll show later in this presentation, and leverage included tools to provide granular visibility into the performance of your system. DeepStream leverages the optimization improvements of TensorRT for inferencing, hardware-accelerated decode and encode using the video codec SDK and multimedia APIs, as well as the raw image processing capabilities when using our Jetson platform. The combination of these components, along with the ability to use heterogeneous concurrent neural networks, simplifies the process to gain rich insights. You can see that we've had previous releases of DeepStream for both Tesla and Jetson. The earlier release for Tesla had limited graph configuration and could only run a single deep neural network. With the latest version 2.0 for Tesla that's available now, we are providing a unified set of APIs that allows you to process multiple streams and run multiple deep neural networks simultaneously. The Jetson version of DeepStream version 2.0 is targeting a release later this year. Now we'll take a closer look at the underlying components of DeepStream. The primary building block is the plugin. It's based on the Gstreamer framework and creates both a simple-to-understand interface but with powerful capabilities. By enabling multi-threaded, parallel, heterogeneous processing, the plugin will provide the most optimized performance. There are typically three types of plugins: source elements that generate data for use by a pipeline, filter elements that have both input and output pads. They operate on data that is received from the input pads and will deliver processed data on their output pads. And then sync elements that are endpoints in the media pipeline. They accept data but do not produce additional data to pass on. The interconnection of multiple plugins create a pipeline for your application. Creating these complex pipelines requires information generated from each of the plugins to be passed to the next plugin for processing. This is what we refer to as metadata. Typical examples of metadata are as follows: an object detected in a frame and the coordinates of that object, the type of detected object, whether it's a car, person, two-wheeler, or road sign, the tracking of the detected object and its unique tracker ID, the classification of the object. For instance, vehicles can be classified further into type, make, model, color, along with license plate numbers. The region of interest, bounding boxes, and text labels that are rendered on the screen. It can also be the number of sources, for example, in a multi-stream use case, and also the number of GPUs used in a system, such that each GPU has a unique ID. The application can probe all of the plugins for metadata and is then used for analytics. Let's now take a closer look at the metadata structure. DeepStream offers an extensible standard structure. It starts at the frame level data, and has an additional subset for object-level data. The GIE unique ID parameter is used to handle scenarios with multiple neural networks where each network gets assigned a unique ID. The numRex parameter tracks the number of objects detected in the frame. And stream ID is used in the case of multiple streams to identify which stream a particular set of data belongs to. The last one is the NVDS object params parameter that contains metadata information specific to each detected object. And I'll talk about that in more detail in the next slide. For each object that has been detected, we have the following parameters. NVOSD-REC-params provide bounding box coordinates for the object. NVOSD-text-params provides label information required for display, such as a white car that's a Mercedes. NVDS-attrib-info has the attributes of objects, for instance, the type, color, and make of a vehicle. Tracking ID provides a unique ID of that object from the tracker. And finally, class ID provides the type of object that it is, whether it's a person, vehicle, two-wheeler, or road sign. One last poll question. The Gstreamer framework is a key piece of DeepStream and the building blocks that we build on top of. We'd like to know how familiar you are with Gstreamer. Please answer one of the options listed. Let's now take a look at how DeepStream culminates into an efficient pipeline architecture based on the Gstreamer framework. This diagram shows the full stack, where each layer consists of software modules, libraries, and hardware blocks. On the top layer, the plugins form core functionality as required by the various use cases of DeepStream. In the next layer, the low-level APIs provide abstraction to the underlying processing engines specific to either Tesla or Jetson, so the various functions can be optimized for the available hardware. So for instance, at the application layer, you just need to specify the need for decode and the source inputs. Then the plugin will invoke the low-level APIs and libraries to use the specific hardware decoder engine that your system has. This is a list of some of the more commonly used plugins that are included in the DeepStream SDK and accelerated using NVIDIA hardware. Many more plugins are available with DeepStream, but I'll be walking through some of these in more detail to help you better understand their functionality. I'll start with the decoder plugin. IP cameras are one of the more commonly installed cameras in various use cases due to its relatively low-cost cabling, long-distance transmission, and bandwidth efficiency. In order to handle these compressed video streams, we built a capable decoder plugin that can support multiple streams simultaneously for two of the more popular codecs, H.264 and H.265. Both bit depth and resolution will depend on the platform and its underlying hardware capabilities. This plugin can be connected to other plugins that accept YUV data, such as the inferencing and video conversion blocks. Before I get into the next plugin, I want to cover the topic of multi-stream batching. TensorRT provides optimal performance when a batched input is received, as it achieves better GPU core utilization. When combining multiple input sources or buffering a single input, it's ideal to form a batch of consecutive frames. It's also important to attach metadata to differentiate between buffers of different sources and that the relationship is maintained when moving between the various plugins. By performing a contiguous buffer for batched operations, it also helps parallelize other functions like conversion, scaling, and on-screen display. In order to help with batching, we've developed this aggregator plugin. This will provide a sequential batched output from n number of YUV input streams and append on any generated metadata. In some scenarios, the input resolution may be different from the desired inferencing resolution that the neural network has been optimized for. To handle that, we've added support for video resolution scaling into this plugin. Next, we have the inferencing plugin that accepts YUV data with optional metadata and outputs YUV data with generated metadata. Generating the metadata is a key function of this plugin and can include things like objects being detected and/or classified. The plugin can run in primary mode, where it's typically trying to detect objects, or in secondary mode, where it may be running a classifier model to identify attributes of a vehicle or person. Today, the supported frameworks include CAFE and UFF models, which is a universal framework format that provides a way to convert models trained in TensorFlow into other frameworks like CAFE2 to a single model format. We understand that some network models are tuned and optimized for data in a certain way. This could be video in YUV or RGB format or specific resolution. So this plugin was developed to handle format conversion, resolution scaling, and image rotation. The next plugin is a reference implementation based on the Kanade-Lucas-Tomasi approach for feature tracking. There are more advanced tracking mechanisms being worked on for future releases that this plugin can upgrade to. The input would be YUV data and the metadata generated from an inference block that provides object coordinates from the initial detection, and will output the YUV data with a unique ID for each object. This plugin also includes an option for scaling and format conversion. For the next plugin, we found that developers both internally and externally want to be able to display all of the incoming video sources into a 2D grid of outputs for debug purposes or to give visibility into what each of the streams are showing in a single view. The YUV and metadata is preserved through this plugin, and the output provides flexibility to configure the size of each video tile. The last plugin I'll cover is for the on-screen display. This allows you to draw lines, bounding boxes, text labels, and other objects on top of the video to help visualize the metadata that's being generated. The YUV and metadata is again preserved through the plugin. Here is an example of the output from the OSD plugin. You can see the purple bounding boxes on vehicles that have been detected, region of interest area shown with the yellow box, and text labels to show the attributes of object type and unique IDs. This is just some of the basic functionality it can do, and we will look at another example later. As I mentioned, I covered just some of the most commonly used plugins, but there are several more plugins that are available from our third-party ecosystem. Whether you have a source that is from a file or a standard vFoil2 device, there are plugins to handle that. There are also plugins for decoding and encoding of JPEG images, along with dewarping fisheye lenses. We have many partners developing additional plugins for various functionalities. Optimized data flow in the DeepStream pipeline is essential for real-time performance and thus the need of minimal buffer copies within the pipeline and ensuring that all buffers are allocated at the proper plugins with the necessary context. This same concept is applicable across both Tesla and Jetson. The data flow is via the Gstreamer buffer, where typically each buffer constitutes a frame. Now in the case of Tesla, the decoder receives data in the form of an encoded bit stream, either from file sources or network streaming protocols. As the decode uses the underlying NVDEC hardware, it allocates a pool of output buffers from the GPU device memory using the CUDA-malloc API. The decoder decodes the frame and stores it into one of the available allocated buffers. This decoded memory is then shared to all of the downstream components in the pipeline, such as the NVINFER and NVTracker plugins, via a buffer pointer enclosed in the Gstreamer buffer. After the buffer is consumed by the sync plugin, the empty buffers are returned back to the pool for processing the next frame. So it's actually the pointer that traverses within the DeepStream pipeline rather than buffer copy to achieve 0 buffer copies in the GPU context. Now, if anyone implements a third-party plugin for inferencing and the plugin adheres to the DeepStream guidelines, then it will automatically ensure that 0 buffer copies happen as well. If the plugin requires data to be accessed in the CPU context, we would need to copy frame data from GPU to CPU memory using the CUDA memcopy API. We provide the same mechanism for shared buffers once the data is in either CPU or GPU space. Now I'll talk about the reference application that is included in the DeepStream SDK. At its core, the reference application demonstrates vehicle identification and attribute understanding like make, color, and type. We use different neural networks for detection and attribute classification, which gives the application modularity and scalability. It starts with being able to handle n number of sources or inputs, which is primarily limited by the hardware capabilities. Typically, the output of each camera is an encoded packetized bit stream over a network. The RTSP plugin depacketizes the encoded bit stream and has jitter buffering implementation to handle network conditions like packet loss and out-of-order packets. Each instance of the encoded bit stream is then fed to the decoder that generates a YUV420 video stream as the decoded output. Then, the inferencing engine that uses TensorRT, which works efficiently on batched input frames, is used, and then we utilize the NVStream MUX plugin that accepts the decoded input and creates a batch of all of the buffers. The primary detector runs at full frame rate, detecting vehicles, its size, and location in the frame, and providing that as metadata. The inferencing plugin can also perform resolution scaling and color space conversion as required. In this example, the network is set up to operate on an image resolution of 960 by 540 pixels, which is half the resolution of 1080p. The tracker is responsible for identifying objects in the frame with a unique ID. It's important to note that the NVTracker plugin uses the unique ID, so it will only invoke the secondary attribute classifiers for newly detected objects and does not waste cycles reclassifying the same object every frame. The secondary classifiers use the cropped images from the primary detector to infer attributes of the object. The output can then be sent to a display subsystem or written to a file using the encoder plugin. In addition, the application can access metadata by installing probes into the respective plugins for cloud analytics. Let's take a closer look at the configuration file for the inferencing block. I'll talk to a few of these parameters, but the full details on all of them can be found in the user guide. At the top, we see GPU ID to indicate which GPU to be used for inferencing in the case of multiple GPUs. For a single GPU, we can leave that at 0. Model file is the path to the cafe model file, and proto file is the path to the proto text file. This contains the network architecture. Label file path points to the text file containing the labels of the objects that can be detected. This could be, in our case, vehicle, person, two-wheeler, or road sign. This file is used by the DEEPSTREAM reference application. Batch size refers to the number of frames or objects to be inferred together in a batch. It's important to pay attention to this parameter as it influences overall speed and performance of the inference engine. Network mode is the data format to be used by inferencing. We can set this to int8, FP16, or FP32. Num classes is the number of classes the model can detect. We are using ResNet 10 with 4 classifier networks. And finally, GIE unique ID is a unique ID that we assign to each inference component so that the application or other elements can understand which neural network this metadata belongs to. Here are some examples of the configuration text file that sets up the system. The top portion shows how to enable performance measurement and some of its parameters, such as how often to sample. The middle portion is how to configure the source of each input, whether it's a USB camera, IP camera, or from a video file. The bottom portion shows the enabling of a sample plugin along with the configuration parameters, such as operating resolution. Now I'll show the application running on a single video stream. This is a single 720p stream running at 30 frames per second. It's showing vehicle detection with a green shaded bounding box along with additional attributes of the vehicle, such as type, color, and make.
As I run the video, we can see real-time detection of the vehicles, the bounding boxes tracking them, and the classification attributes in the text labels.
Now you can see 25 HD streams running in parallel on a single Tesla P4 workstation. For each stream, we're running the same object detection, tracking, and classification happening in real time.
Here is the video of the 2D grid of 25 HD streams being processed simultaneously. You can see the vehicles being detected and tracked all at once.
Configuration that was used to run this application. You can see it's a standard server class CPU with a single Tesla P4 GPU. On the right, we show the utilization numbers for the GPU, memory, encoder, and decoder. Considering that we are processing 25 720p streams running at 30 frames per second, and each stream has a primary detector, a tracker, and 3 secondary classifiers, all while displaying the streams in a tiled display, there is still a significant amount of capacity left over in the GPU. This would likely indicate that we could run additional networks per stream, but may need to adjust resolution and/or frame rate to bring in additional streams due to the higher decoder utilization. The primary goal of DeepStream is to help accelerate development of IVA applications, but performance plays a key component to developing your application. I'll talk through some of the main concepts for quantifying performance, then discuss methods for measuring and optimizing performance. First, let's look at some of the key performance indicators for measuring system performance. Throughput can be thought of as how many frames can be processed in a unit of time. Frames per second is a typical metric. Latency is measuring the amount of time it takes for a frame to traverse the entire pipeline. We have many different hardware components, from the decoder block, the GPU, memory, and the different interface buses. Being able to appropriately load each of the hardware blocks is important. And finally, power needs to be considered depending on the application and platform being used. For instance, the requirements will likely be different for a Tesla-based server versus using a Jetson on the edge. Let's look at the benefits of optimizing performance. Increasing throughput allows you to process more frames, which can equate to either processing your existing video sources at a higher frame rate or allow for more video sources to stream to a single GPU. From a system perspective, this can help reduce the number of GPUs needed, thus decreasing the cost of installation. Shorter latency can provide better real-time reaction to events. Here's an approach we recommend for analyzing performance. First, set the KPIs that are critical to the system and understand any gaps in the expectations compared to the reality. We offer tools like NVIDIA SMI to show utilization of each of the hardware blocks that will help identify bottlenecks, which I showed earlier for the reference application. I'll show later how latency through each plugin can be measured using log files. And we have a number of other tools that help view system-wide performance. We see many developers build plugins independently without realizing that they may be competing for the same resources. So it's important to look at the full system pipeline. To measure throughput, we use probes to get a sense of the data flow. For the input port of the display plugin, we can install a probe that will log the time it takes for a frame to pass through this plugin. This can generate metrics such as average, maximum, and minimum frame throughput at a granular level for each video stream. In this example, we are looking at a section of the log file for a particular instance of the decoder plugin latency. You can see the time a frame entered at the input of the decoder plugin to when it entered the next input is 33 milliseconds, which would equate to roughly 30 frames per second. Performance optimization is often dependent on specific system and application use cases, but here are some general guidelines that we have seen help improve performance for many applications. For inference, we found that reducing precision from FP32 to FP16 or into 8 can shorten latency and improve throughput. The loss of accuracy from the lower precision is often negligible. Also, batching many frames for inference can help reduce the cycles needed per frame and increase throughput. One trade-off is that batching can increase latency, so you need to determine if this is appropriate for your system. For slower moving videos, decreasing the processing frame rate can help with throughput. For example, if you have a 30 frame per second input, you may not need to process every frame, but actually processing a frame every 2 to 3 seconds can still yield a representative sample of what's happening in the scene. As discussed earlier, we have an efficient system for managing memory within the GPU, but it's best to minimize data movement between GPU to CPU and system memory. And finally, using CUDA streams to decouple computations that aren't dependent on each other and running them in parallel will help overall system performance. Now let's talk about custom plugins. Adding custom plugins can be very useful to import newer, more accurate, and efficient network layers based on TensorRT for inferencing. In the next several slides, I'll walk through the steps required to add a custom plugin layer for object detection based on the YOLO architecture. At a high level, you'll first need to train your model independently according to the specifications of your application. Next, import the model into TensorRT and build the TensorRT engine. Then, wrap the TensorRT engine with the included template DSExample plugin and ensure that the output bounding boxes from the network will be attached as metadata. Finally, once you have your custom inference library set up, just disable all the default inference modules, enable the template plugin in the config file, and run the application. The sample DSExample plugin provides the framework to process an entire frame with an option for downscaling and color conversion. It can also act as the primary detector for objects and provide bounding box coordinates for the objects. Here's what a standard pipeline would look like, but notice that the standard NVINFER plugin is disabled, and we've included the custom plugin. This custom plugin would act like the standard NVINFERENCE detector plugin by receiving the image, sending it to the inference library, which returns the bounding boxes for every image, then attach it to the metadata and send it to the next plugin, like the OSD module, for drawing the boxes. One reason someone may want to take advantage of this capability would be to use the YOLO v2 model architecture. YOLO, which stands for You Only Look Once, is an open-source convolutional neural network that has recently grown in popularity as a very fast and accurate real-time object detection network. The input to the network is an RGB image, and outputs contain the bounding box info of the objects within that image. YOLO is natively trained in DARKNET, which is an open-source neural network framework similar to Caffe or TensorFlow. The primary recommended approach to import a model trained in DARKNET into TensorRT is through the TensorRT Network Builder API. The user would define the network by adding various layers and their corresponding weights directly into the network and build a TensorRT engine. Detailed information on this can be found in the TensorRT SDK documentation. For those of you who are familiar with the YOLO architecture, we know that it uses leaky ReLU, a reorg, and a region layer, but these layers are not natively supported in TensorRT version 4. The solution to this problem is a plugin factory. A plugin factory encapsulates all the plugin layers which are being used in your network. This object will be used by both the parser and runtime to add the plugin layers when the network is being parsed and deserialized respectively. The users have to implement the interfaces used by the parser and runtime to add these layers in the network. The samples in the TensorRT SDK provide a good introduction on how to use a plugin factory. For the YOLO architecture, the TensorRT SDK has already implemented the above 3 plugin layers. There are a few caveats to keep in mind when using them in your architecture. First, there isn't a specific plugin for leaky ReLU, but there is one for a parametric ReLU. We can use this by setting the slope to -0.1, and it will behave similarly. Second, the region layer plugin computes only the logistic activations and softmax scores on the input tensor. And finally, decoding the actual objects from the various predictions of the network should be handled outside the TensorRT engine. Now that we've covered the reference application, let's walk through the thought process of building your own application and leveraging the DeepStream SDK. The first step is to have a strong understanding of your use case and having clearly defined requirements for your end goal. You'll need to think about what operations will be needed and how those can be mapped to plugins. In the example shown, we're trying to build an object detection and counting application. You can see the mapping of the functional blocks to actual plugins. Next, you want to think about the expected input and output for the entire pipeline, but also at the individual block level. So you want to account for the source types, image formats, and metadata that's being passed through the plugins. Then check if the functions or blocks that are needed for the pipeline already exist as reference plugins that come with the SDK. For any functions that aren't included, you can create a new plugin for which we have a plugin implementation guide to help. Finally, you want to consider the performance expectations and any constraints there might be. Lastly, let's look at a fully modular application based on DeepStream. On the input side, raw or uncompressed video can be streamed from cameras and leverage the Jetson image processing capabilities to convert to YUV data. We discussed bringing in encoded streams from IP cameras, but that can also be previously reported stored video. Other non-video sensor data can be brought in as well. Next, we talked about the decoder, but additional image filtering and pre-processing can be added as a plugin for things like dewarping fisheye lenses or noise filters. Along with the included plugins for inferencing, support for third-party plugins is available to handle the growing ecosystem of plugins being developed for various use cases. Whether you are well underway in developing an IVA application or you are exploring potential opportunities, DeepStream can help you accelerate your IVA application development using deep learning on NVIDIA hardware. Please visit our website to learn more about how to download the DeepStream SDK, explore our Metropolis platform for smart cities and the large ecosystem of partners, and collaborate with other developers on our IVA forums. Thanks for attending this webinar. We'll now go into our Q&A session. And now we'll move into a time for questions. Please submit questions if you haven't already, and we'll read through and answer them. All right, thank you guys for attending that first part. We'll talk about some of the questions now, and we received quite a number of questions, so we likely won't be able to answer all of them, but we will be able to answer them afterwards during the on the forum. So don't worry about the questions, and we'll certainly look at all of them. I'll address a few of the key ones that we've received so far. A question we got a lot was about running DeepStream on GeForce 1080 type cards or Quadro cards. The DeepStream SDK is focused on the Tesla product line, so after the Pascal version of the GPU architecture. That's to say we don't test on GeForce or Quadro, but you're welcome to try and get that working, and we won't. There's no blocking in the SDK for that. Another question we got was about how to load balance the use of different GPUs in one system. And so you can run different pipelines in different GPUs within your DeepStream application with the current release. And dynamic load balancing is planned for a future release. We have another question about metadata that's generated by the plugins in the graph, and whether that means labeling and annotation is not required for training purposes. So DeepStream is focused on inference, and the metadata is internal to the application. So labeling and annotation of the data for neural network training is still needed. Another question we got was about the YUV data that's the input to the plugins. And it sounds like this person uses RGB video streams. So all of our plugins generally do accept YUV data, but we do have a color space conversion plugin that can convert RGB to YUV to input into the plugins. All right, there's a question about instead of outputting to a display, is it possible to create an RTSP stream as the output? And the answer is yes. You can encode and stream the output, and you can use one of the standard open source plugins that are available. And we're looking to provide this as a standard plugin that's included in the SDK in a future release. So the question about the which P40 or which Tesla product was used for the example, and I did mention in one of the slides that we use a Tesla P4, but DeepStream can be run on any Tesla product, so P4 or P40 would work. Looks like we're getting a question about the development environment, and we're targeting Linux as the primary development platform. I think we have a question. Is the inference engine limited to certain neural network frameworks such as Caffe? Does it support TensorFlow or others? And what API does it use the frameworks through, and which frameworks are supported? So DeepStream uses TensorRT as the inference library, and any network that's supported in TensorRT will work in DeepStream. So that does include Caffe and TensorFlow, and others are targeted for later releases. Got another question about performance. So the flops and frame rates that are typically supported. So performance, as I talked about in the slides, are definitely dependent on the application. So which networks are being run, how many networks, and any other custom processing that's needed on the GPU. And the reference application is a good example to show 25 or 26 streams running on a single Tesla P4 card with several networks running for detection, tracking, and secondary attribute classification. Yeah, it sounds like we're getting a lot of Jetson-related questions. As I mentioned, Jetson is, we have a version 1.5 available today, and the version 2.0 for Jetson, we're targeting for a release later this year. There's a question about streaming the metadata out. So we do allow access to the metadata at each of the plugins. So certainly you can stream the metadata out in various ways. And that metadata is transferred from plugin to plugin and is available. Yeah, I got another question about what happens if the GPU reaches its processing limit and I keep adding cameras. How does it handle overloading? So again, this is where you need to measure performance and the utilization across the different processing engines. I talked about a few different methods for handling that overloading, whether it's decreasing the number of frames that are being processed, decreasing either resolution or the number of networks being run. But it's important to keep in mind the performance requirements for your system and handle based on your system configuration. Getting a lot of questions here. I'm trying to filter through all of them. Can we use DeepStream with normal CPU like an i5? And yes, where there's no limitations on what CPU is being used. So it's focused on the GPU portion, so the Tesla product line. And I think certainly a CPU like the Core i5 would work. Is it also available on the DGX1? And we are, again, focused on the Tesla product line. But that's not to say we wouldn't block you from trying on a DGX. Okay. So it looks like there's a question about supporting YOLO version 3. And yes, we will be able to share a GitHub link to enable that. Okay. There's a question about CUDA 8.0 compatible with DeepStream 2.0. And the answer is no today, but that's something we'll definitely look at for future releases. There's a question about, is the software open source, free, and what are the license terms? And it is a free software. Yeah, so it's free and not necessarily open source at this point, but there are no licensing fees associated with it. Okay, there's a question about DeepStream without Tesla or Jetson GPUs. So DeepStream is specifically designed to run on NVIDIA GPUs and specifically the Tesla and Jetson versions. So all of the plugins that are hardware accelerated are targeting the GPUs for Tesla and Jetson. So a lot of the hardware acceleration may not work with other processing components. So I would say that it is definitely targeting for NVIDIA GPUs, and we're not guaranteeing any kind of support or performance for other GPUs. Okay, let's see. Still looking through your questions. Can you download the presentation? So yes, we'll have links to the question or presentation as well as other resource links. After the presentation, you'll get an email on that. I see people asking about the Jetson version 2.0 features. All of those are still being planned out, and you can imagine somewhat similar functionality to the features and plugins that are in the Tesla version, but just customized for Jetson. There's a question about performing profiling on DeepStream. So we do have performance tools that I talked a little bit about and to determine utilization for the different processing blocks. So for the GPU or for the decode or encode engines, as well as the memory bandwidth, all those can be seen using the NV performance profiling tools. Still looking through the questions. Okay, there's a question about the third-party ALPR plugin. So that is one that we work with one of our ecosystem partners on. We should be able to provide more information on that after this, but we have tested that and are seeing some good results with DeepStream. So that's just one of the first few third-party plugins that are being made available. I have time for maybe just one more question. Is there a workshop for DeepStream 2.0? So we did just roll out DeepStream 2.0, and we're certainly looking at opportunities for workshops and training classes, both in the different regions. So we'll certainly email you any information about future events that we're planning. Okay.
Thank you all for attending today's webinar, and thank you, James, for presenting and answering all of our questions. As we've already mentioned, we're going to have a recording of this presentation, and that's going to be emailed to you later today. Don't forget to become an NVIDIA registered developer to get access to all of the latest news and products, software, and more. And thank you again for joining us today. We look forward to you being with us at our next event.